Hi there, thank you for being there to watch my final report. Let's get started. First of all, the topic of my project is a novel peptide-based method for virtual screening to discover drugs. Let's firstly focus on the word virtual screening. So, what is virtual screening? Virtual screening is a computational technique used in drug discovery to search libraries of small molecules in order to identify those structures which are most likely to bind to a drug target, typically a protein receptor or enzyme. We can just simplify the whole process to be like finding out a ligand in a small molecular library using computer. The reason why we use virtual screening is that chemical space is vast, which means that large numbers of compounds should be tested to get any results, but only a very small proportion of them are available compounds. If the test scale is large, it will be very expensive and time costing. So, the virtual screening takes advantage of computer simulations to predict the ligands, reducing real laboratory experiments and accelerating the drug discovery process in a more efficient and economical way. After specifying the importance of using virtual screening, let's then simply talk about the possible virtual screening techniques so it's to get to know which one should be used in our project. The virtual screening can be divided into two parts, ligand-based virtual screening and structure-based virtual screening. The difference between them is proposing a new ligand based on the existing ligand or the binding pocket of the protein. Okay, let's move to the similarity searching of the ligand-based virtual screening part. The similarity-based virtual screening searching will give a ranking order based on the similarity to the reference, but the reference here is very subjective. For example, we got strawberry, watermelon, basketball there. For strawberry and watermelon, they are property similar, while for watermelon and basketball, they are more structurally similar. However, we could say they are all similar, like strawberry is similar to watermelon and basketball is also similar to the watermelon, but with different reference. The similarity measure can be simply divided into three components. The first step is setting the molecular descriptors used to calculate the similarity coefficient and weighting functions so as to gain the ranking order. And the molecular descriptors can be different based on different situations, like physiochemical, 2D, 3D. And the rationale behind is that scientists believe that structurally similar molecules tend to have similar properties. So, the similar property helps us to get the ranking. Let's then talk about the pharmacophore mapping part. It is using all necessary steric and electronic features to ensure the interactions with specific target, the protein, and trigger its corresponding response. And the main things to look at are hydrophobic bond donors, hydrogen bond acceptors, sp2 hybridized, lipophilic, size, charge, and electron positive or negative, as you can see in this graph. The basic steps for the process for pharmacophore mapping are firstly, to find out the pharmacophore features in each ligand identified. Then select the ligands having corresponding features at a conformational scale in the library by being overlaid with the aimed ligand. Then it will also give us a ranking by the pharmacophore hypothesis. In all, we can conclude that we will use the pharmacophore mapping when predicting how the ligands will bind to the receptor without knowing the structure of the receptor. For the machine learning, the ligands will go through the substructural analysis, recursive partitioning, support vector machines, k-nearest neighbors, and neural networks to get a ranking based on the likelihood of being active ranking. Lastly, moving to the protein ligand docking of the structure-based virtual screening part. Here are the two key component search algorithms. First one, ligand atoms are matched to sphere centers so that distances between atoms equal distances between sphere centers, which are used to position the ligand within the active site. Secondly, because of the conformational change, there might have many poses, but we will get ranking using the scoring function to score by the goodness of fit, and the highest scoring pose will be presented to the user. After stating the basic ideas about all the possible virtual screening methods, let's move back to my own project. I highlighted peptide-based method and discover drugs. Tell me the details of the method and the aim of ours. Use peptide to find the ligands which have the potentiality to be drugs. And for drugs, we need to find out the aimed protein, the protein binding site, and the ligand and the peptide. After knowing the concepts about both the virtual screening and the aim of project, we can conclude that firstly, we focus on the peptide because we don't know chemical ligands. Secondly, the peptides should have similar property as the ligand, so they should have similar structures. Thirdly, we know the important pharmacological features. Lastly, the ligand comes from random library. To analyze them, we don't know the ligand and the details about the binding site, so we cannot use structure-based method. Secondly, we only know the important pharmacological features. Lastly, we do search in random library. The three key clues tell us we should use the pharmacological mapping. So the virtual screening for pharmacological mapping should be changed a little due to the use of peptide template, because the aim is to see whether this method works or not. So we should find out the protein both have ligand and peptide. What's more, since they should have similar binding structures, they should be overlapping when superposing two protein structures. For these real existing overlapping ligands, we should try to make as many conformations as possible, then to see how they are precisely overlapping with the peptide to have the appropriate cutoff value. And then the aimed ligand here should be the peptide template, but only keep the useful pharmacological features as the template. This template then will be used as a reference to get a ranking based on the similarity to its pharmacological features. If the results show that this method increases the probability to find out the real ligands among billions of random molecules, it accepts the hypothesis we set. And if the hypothesis is true, we could use this method to search for specific trigger ligands among large libraries. I use the highlighted words to make an easier looking version. Say the process again. So the first step is to find out the proteins both have ligand and peptide and they are overlapping. Then keep the pharmacological features as a template. After that, firstly use the template to go through RIDE. Here, RIDE is a fast 3D molecular similarity search method based on atomic property fields, but quicker than APF. APF is a method for ligand-based virtual screening using the chemical properties or pharmacolophos of ligands, just as what we talked about at the pharmacological mapping part. And the reason why RIDE is quicker is that it firstly converts all 2D ligands into 3D structures needed for APF. Use a template to go through RIDE to see how the ligands are overlapping with peptide. Both checking the template, ligands, and get the cutoff normalized score. If everything is good, especially the normalized scores, then use the template in a bigger library to see how many ligands have normalized scores higher than the cutoff value. Then use the data and the number of the real ligands and the number of small molecules in the library to calculate the enrichment value to see how the method can increase the probability to find out the aimed ligand. And I divide the whole process into four main components. The first one compile a list of proteins that have a binding site with both structures bound to the peptides and structures bound to the ligand. At very beginning, I just searched the cyclic inhibitor protein because for these proteins, they are more simple structured and they definitely have an end protein. However, due to the special case, I need to find the proteins both contain ligands and peptides at the same time. What's more, they should even be overlapping, but that is so time costing and inefficient. So then I looked at some review papers to see what proteins they had used to get a good result. Here comes up with one question. I don't know the standard of overlapping. To what extent can we call it overlapping? So I included all of them at first for those who are overlapping very well and those only overlap at 1 or 2 atoms. But after trying through all the proteins, the result shows that the requirement for overlapping should be constrained at overlapping at the important functional groups and the carbon chain. Let's see how the overlapping looks like in the proteins receiving positive results. We can tell that both of the functional groups and the carbon chains of peptide and ligands overlap well among all of the 3 proteins. Only if some important functional groups and carbon chain are overlapping can we use it as a possible example to go through the later process, the right, as we can see in the pics. Then see how the bad overlapping looks like at the bad examples. Whereas for this protein, only the green spotted atoms overlap. Neither functional groups nor carbon chain overlap well. So that is the main reason for low scores in that prediction. So this kind of protein cannot be used as an example to prove that the peptide-based method is useful. Let's dive to see which proteins are actually overlapping badly, except for the first 3 proteins had already showed good overlapping examples. And we'll use the ICM to see other examples.
Okay, let's see for the BCL2 human proteins. The yellow part is the protein and the orange part is the peptide. And I already deleted the non-related atoms, and the leftovers are the important pharmacophore features. And we can see that for the real ligands, it seems that they are overlapping very well. However, if we zoom in and just zoom in to see that the important functional groups and the carbon chains, none of them are overlapping actually, we can see. Only this part and here are overlapping. For other examples, other ligands, it's like more obvious to see that only a few atoms are overlapping. It doesn't like satisfy our requirements, so the BCL2 human proteins cannot be the example. Well, for the third one, human protein is actually very easy to see. The gray one is the peptide, and the green one here is the real ligand. They are just like very similar place, but they're actually not overlapping at all, as we can see here. Like none of the atoms are overlapping. So obvious, the SIR1 protein is not a good example. Also for the other other ligands, as you can see, none of them are overlapping well. Yeah, so one is definitely not a good example. And for the trypsin protein, it's kind of like tricky. Again, the yellow part is the peptide and the light pink part is the ligand. As we can see, it looks like they're overlapping quite well, especially for the carbon chain, right? However, we can see more precisely for the ligand, we can see the important functional groups. three of them, literally none of them are overlapping very well. So sadly, the trypsin protein also cannot be the example. And for the kaolin 4 protein, it looks like for the carbon chain, they're overlapping well. However, the ligand is actually a little bit too small, so it's not very like representative. But also the functional groups are not overlapping. As you can see, there's no functional groups there. So sadly, it also cannot be used as an example. So for search human protein, we can see here the yellow one is the peptide, and the background is the protein. And we can see how the ligand interact with the peptide here. It's it only like overlapping at these three atoms there, so it's definitely not useful. So let's move to another ligand. Also, it seems like none of the atoms are overlapping. Another one seems nope. Nope. Also, only one atoms probably. So definitely no. Also here is also nope. So the third two human protein is also definitely not a good example to go through the later process. The last human protein here, these overlapping parts means that they have the same protein structures. So let's do not see that part. Okay, let's focus on the peptide and the ligand. The yellow one is again the peptide. The dark blue one is the ligand. We can see only one part of the functional groups are overlapping for the carbon chain, and the another part of functional groups, neither part of them are overlapping. So sadly, RAS human protein is also cannot be used as the example. So for the PLK human protein there, we can see it seems that they are overlapping very well, but it's only about the carbon chain. The important functional groups had nothing to match with. So the PLK human protein is also not a good example. Okay, for the cap protein there, we can see the yellow part is again the peptide, and the leftover atoms are the important pharmacological features. We can see the dark red there are the ligand, and let's see more clearly about the interacting. We can see it looks like they are twisted. However, the only overlapping parts are a few atoms again here. So obvious, you can see for other ligands are the same. Oh, sorry. Non-ligands overlapping well. So the cap one is not a good example as well. So for this non-human protein, we can see that yellow part, the peptide, and with different ligand, we can check that both neither the functional groups nor the carbon chains are overlapping. Like for all the ligands are the same. However, as you can see here, for the result here, it shows that for this 2I and B here, for this protein, for this ligand here, the prediction based on that is actually pretty low, pretty high, due to the high normalized scores. So what's the reason for that? So we can see from here, Here, this part of the peptide and this part of the ligand, as you can also see here down there in this chart. Here, it is actually the same functional groups, the guanidine, and also the same carbon chains there. So the prediction goes like this. It's also pretty short. So that's the main reason for making this a good prediction, but that's an exception. Should not be counting so as to make this protein as a good example. Still no, because for other situations, the normalized scores are pretty low. So yes, so this non-human protein cannot be a good example as well.
After deleting the proteins that do not have perfectly overlapping peptide and ligand, we only have 3 possible proteins left. Then, next step is to set the peptide template, which is set to keep the pharmacophore groups. And here's the simple criteria I set for keeping pharmacophore features and their connection atoms, only using 3 proteins having peptide and ligand overlapping well. And we're using an example can be applied with all the rules here. Okay, so roughly read through the process. Firstly, roughly determine the selection range. Then use IC inversion to see the binding property to determine which part is important due to the interaction. Hydrophobic region, the most important. Atoms that have important interactions. Lastly, if the template was still too long, we like to compare these parts to choose the most hydrophobic part or the part mostly goes deep in cavity. And we'll use MDM2 protein as an example to go through the whole process. First, roughly determine the selection range, delete the unrelated atoms. So we chose the first 3 cavities and delete the unrelated atoms. Second, use the IC inversion to see the binding property to determine which part is important due to the interactions. Hydrophobic region, most important. Atoms that have important interactions. Here, most are surrounded by the green region, meaning the hydrophobic region, so we just keep the atoms having a hydrogen. If the template was still too long, we like to compare these parts to choose the most hydrophobic part, or mostly goes down in cavity. It is too long, and for the middle one, it is deep down in protein. For the other 2, the left one is more hydrophobic. Then we just use the pharmacophore mapping method to have the ranking of the molecules. And there are several settings we should pay attention to. The first one is while converting 2D ligands to 3D, which is because of the conformational changes. We usually set it into 30, and the APF cutoff value is the lowest normalized score we got from the real ligands list. What's more, we often use envelope and exclusion of the protein atoms to get rid of some distractions. Okay, let's step to the last place, calculation. We often take the one having normalized score around 0.5 or even higher as a cutoff value for easier calculation. So the number of the good real ligands is 1. Number of real good ligands containing both the real one and the 2 in the random library. And the number of real ligands I have found is 5, and the whole ligands in both library and the real 5 ones are 972. So we can have the enrichment value is 64.8, meaning using the method, we can have increase of 64.8 times probability to find out the real ligands. I had concluded the data results received from the 3 successful examples. The blue bar means the number of small molecules in the random library. The left blue bar of each protein represents a smaller library, while the right bar means the larger library. The orange lines shows the trend of the enrichment value. As we can see, it increases as the library increases. But from this data, it is not very obvious to tell the relationship between the enrichment value and the number of small molecules in the library. So I made a scatter plot to try to find out the regularity behind. We can roughly say that the difference of number of molecules and difference of enrichment values are correlated, but we need more examples to make it more precise. Except for the problem that there are too few successful examples, we could say that the peptide-based method might be useful to increase the probability to find out the end ligand among billions of random molecules, but with the restriction that proteins need to have structures having overlapping peptide and ligand. Hope in the future there will be more examples to prove this method is useful. Thanks for the help from Dr. Shapira, Avian, Mandeep, Jessica, and Marco. Thank you for watching.
Okay, so firstly, load the protein structures having the peptide. We can see here's the protein and here's the peptide, and we want the stick version. And then load the first picked ligand. Okay, and firstly, let's see how they are superposed, whether they are superposing with each other, and it shows that they have the same structure, meaning that they are the same protein. And then we'll see how they are overlapping with each other. Zooming to see. Here we can see that the carbon chain overlap very well, and here the important, and we can see that at the important function groups, they are also overlapping with each other. So probably it can be used as the it can be used as the example to go through the later process. So after loading the five ligands, five real ligands I chose, and make the protein of them superpose these with each other, and I should then just like abstract the ligands into a separate list. All of them should be. After the first one, the later four ligands should append to the existing table. And so you can see they are all existing here, the five ligands there. The next step is to reload this or like resave it into, resave them. Let's see. I'll right click and you can see save as, and you just have another name of it. Because I already have the, let me see, this protein, and this is the one that I used like in March. So in May, so I will just like have another name, Shep ligands 2D. Okay, save them. And I should convert all the 5 2D structures into 3D structures, and we can find it in here, chemistry, generate 3D conformers, write database. Like input files is what we just saved. So here and output. Surely we place them into the same file. because that's much easier to find out. Use sharp ligands 3D. And usually we just set the max number of conformers into 30, that's enough. But in some cases, if you find out the result is not what you had expected, so probably set them into a bigger number, but normally 30 is enough. And we just wait for the process. After having the 3D structure of the real ligands, we can just keep what we should do for the right. So the first step is to change the protein into ICM version, and then change the meshes into both plain solid and also the version we can see the binding properties, so we can check for the peptide template. So after we did all the preparation, and we can see the binding properties right now. Firstly, we can see that the peptide are directly overlapping with the protein. That's obvious. So we just focus on the selecting range, as we just said, the criteria for keeping the atoms. So firstly is roughly determine the selection range. It's very actually it's very clear to see that owning this is a very a big cavity because it's very small, and honestly it's a little bit too far from this dense area. So probably these areas should not be considered very clear very much. And also we can see they are not very dive into this cavity. So probably we should not consider this cavity. And then we'll use the ICM version to see the binding property to determine which part is important due to the interaction. Firstly, it's about the hydrophobic areas. So we can see here are the hydrophobic areas, and not very much of it. So also here has a little bit. And also the atoms have important interactions. As we can see, these oxygen here definitely are form the hydrogen interaction with the hydrogen inside it. But also here it's very clear to see that the blue region with this red hydrogen atoms here, and also here, as you can see, and here. So we'll keep this because these are the hydrophobic areas, and also it's an important functional groups. Also, we should keep all of these atoms there because they are all interacting. They all have the important interactions. Not there. There is a little bit too far from inside. Keep there. Not this one. This one is close to the hydrophobic area, so we should not keep this one. This one, keep it, not this one. And this area is honestly a little bit too far. So for these regions, we should keep the occupancy into 0.001. So the reason is the reason why it's not 0 is because something wrong with this. It's probably because of the system, but it's not that, it doesn't really matter. Okay, so I keep this, and this one. Miss it. 0.011. And you can see all these labels shows that these are the atoms that I set the occupancy into 0.001. So yes, after keeping setting all these atoms should be kept, then we'll use them as the as a peptide template to go through the right. Okay, let's just go through the right. Right. Here. And the cutoff we just set it not to be very high. Use exclusion of the protein to get rid of some extractions. Also use display envelope to do so. And go through right. So here's the result. We can see that we just set the cutoff into 0.3. So 3 of them are above this score. And here the 0.33 is a lot lower than that. So probably we'll choose the 0.42 as the cutoff value. So we can see that this normalized course is pretty good though. So we can just go through the later process, which is to use it in a bigger library. And it's almost the same process as before. Research, only the 3D conformer database is different, using a bigger library. Still, the cutoff here is 0.42 though. Yes. And display envelope, use exclusion, and let's go. And using the number 12 here, and just like use a plug plug the number here into the equation, we got the enrichment value to be 28. It's not that high actually. Probably it's because the process is a little bit too fast. So, but the whole process is what I just did, and then use the cutoff value to go through a much larger library to get what it actually showed in the real life. So it's the basic steps, though the process of mine is a little bit not that perfect. So yes, that's it.